This is the second lecture of Chapter 6, which deals with solutions and colloids. Just a quick review before we actually start today's lecture. Last lecture we looked at solutions. We actually defined solutions as made up of a solute and a solvent. Then we looked at types of concentrations. So in other words, concentrations can be measured differently. And two that we actually looked at was the percent weight volume. Notice how it's written, percent weight volume. So you should be able to determine the concentration of a solution using this unit here. Next, we looked at the molarity. That's another unit of concentration that's typically used in chemistry, the molarity, and it's defined, of course, by the number of moles in the volume, which is in liters. And lastly, we looked at dilutions of solutions. And of course, that's a very important aspect in chemistry, in science, period, because typically we get a stock solution that's purchased from the pharmaceutical company or from the chemical industry, and we have to dilute it before we actually use it. So let's look at today's lecture. So in today's lecture we look at colloids, and that's another type of solution that we'll define in a second. And then we look at properties of mixtures. And the main ones that we look at here is freezing point depression and boiling point elevation, and of course osmosis. That's of practical importance in today's world. Okay, let us start by defining colloids. In true solutions, the maximum diameter of the solute is about 1 nanometer. So just imagine here a true solution of sugar and water, where the water is a solvent and the sugar molecules are the solute. As you can imagine, the sugar molecules are really small. But if we have a solution where the solute is much larger, going up to 1,000 nanometers, that's no longer classified as a true solution. There's a different term for that. We say that's colloids. So colloid here is a solution that's made up of solute where the particle size is much larger than that of your true solution. So the properties of colloids are shown here. They have large surface areas, the particles. Now we're going to call these particles and not solutes per se. So the colloid particles are large, and they have two characteristics. Number one, they scatter light. So if you shine light through a solution that's a colloidal solution, it scatters the light. So it looks a bit turbid or cloudy, and are often described as milky. Notice that's different from your true solution, which would be like a solution of table salt in water. Another aspect here is that they form stable dispersion. In other words, they do not settle out of solutions. They remain suspended in solutions, but you can't really settle, it's not really settled out as a precipitate. So in other words, you can't really filter it and see. All right, let's look at some examples. So the first example here is, let's look at this one, for example, whipped cream. That is a colloid solution which we have gas in a liquid. So whipped cream is really air in milk. Another example here is smoke, for example. That's solid particles in gas, in air, for for example. That's why we can actually see it. So these are just some examples here. Another one is fog, which is really liquid water vapors in air. So that's a definition of fog. So these are all described as colloidal mixtures here. Let's look here at comparisons. So here let's compare a solution, a true solution, with colloids and suspension. Okay, so just imagine here a suspension would be, I don't know, you go in the kitchen and you mix salt, you mix pepper, for example, black pepper and water. And here, this would be mixing here for example, your milk in air, and this would be your typical solution here, which would be salt in water. The particle size, as you mentioned, of the solute, pretty small, colloids a little larger, and suspensions, they are even much larger. Can you filter off the solute from a solution? No, you cannot. In a colloid, you cannot. But in a suspension, you can. So if you had, for example, black pepper mixed in with water, yes, you can filter off the black pepper. Homogeneous, a solution, yes, it is homogeneous. A colloid, it's borderline, homogeneous versus heterogeneous. And of course, if it's a suspension, it is not homogeneous, heterogeneous. You can really see both aspects of that solution. And the last one here is settle on standing. No, you have a solution of salt and water. You have it sit overnight. It still remains a uniform solution. You have a colloid. You have it sit overnight. You come back, whipped cream, for example, the next day. It is still whipped cream. But if you have a solution of black pepper, getting back to my example, black pepper and water, you come back the next day, you'll see the black pepper at the bottom and the water at the top. So it's separated out. Behavior in light. So you shine a light through sugar and water, transparent. You shine a light through colloid, the light scatter. We call that the Tyndall effect. So the light will scatter. And of course, if it's a suspension, it's translucent or opaque, which means the light is blocked. It doesn't go through it. So these are the differences here. So what you should get from this slide is, if given an example, salt and water, is that a solution? Is it a colloid, or is it a suspension? So again, think of practical examples in the lab or even in the kitchen, and try to classify them as solution, a colloid, or a suspension. That's part of the thinking process, part of the process that gets you curious and analytical, and the process that gets you to categorize your understanding. Okay, let us go into a property here called colligative property. So based on our approach here, let's define that property, make sure we understand it, and then we will apply that to solving different problems. So colligative property, by definition, is any property of a solution that depends on the number of solute particles. Keyword here, number of solute particles, and not on the nature of the particle. For example, if you have a solution that's made up of table salt and a solution that's made up of sugar, the colligative properties should be similar. Okay, so the properties that we'll examine for the next few slides will be freezing point depression, boiling point elevation, and osmosis. So these are now properties of solutions. Properties of solutions that are called colligative properties. One practical example here is in the winter time, we, of course, as you know, there's ice on the road, And if you drive on the road, you start skidding around because you're driving on ice. But if we should put salt on the road, for example, this truck is putting salt on the road, it literally melts the ice, and so we're literally driving on water instead of ice. So that happens every winter, especially in areas where there is lots of snow. But let's see what really is happening here from a chemistry point of view. So we call this freezing point depression. So what happens is the freezing point of water is, of course, as you know, 0 degrees C. If the temperature gets below that, we have ice. We don't want to drive on ice. So if we can get water to freeze at a lower temperature, then we have more water around. So here's one property, colligative property, and that's the freezing point depression. By definition, so 1 mole of any particle dissolved in 1,000 grams of water lowers the freezing point. So if you put a mole of any substance, particle, in 1,000 grams of water, the freezing point of water is lowered. It's lowered by minus 1.86 based on this definition. So here is our conversion factor here if we need to carry out the calculation with different concentrations. Notice here the key word again is moles. So it's moles of particle. So as you can imagine, if given grams, weight, the first thing you'll have to do is to convert it to moles to use this equation. Okay, so again, let's point out here we typically put sodium chloride on the road, salt, or calcium chloride, another type salt, to melt ice so we can drive on the road. Another important application of freezing point depression is in the we have here ethylene glycol antifreeze that we put in the radiator of cars, and that of course lowers the melting point of water. So let's see if we can apply this concept here. So first, let us look at this example. If we had add here 275 grams of ethylene glycol, which is antifreeze. So we have here 275 grams of antifreeze. Here's the formula. Of course, now you know why we give you the formula, because we're going to convert things to moles. And that's per 1,000 grams of water in the car radiator. What will be the freezing point of that solution? So we want to lower the freezing point. So in the winter, the water in the radiator doesn't freeze. That's why we have antifreeze in our cars. So let's look at ethylene glycol. This is a molecular compound. What that means is it's not ionic. So when it's dissolved in water, it gives 1 particle. Just for comparison, if you dissolve NaCl in water, it gives 2 particles, sodium plus, cation, and Cl minus, the anion. 2 particles. But if you dissolve here ethylene glycol, you get 1 particle. Okay, next we need to convert the mass into moles. So first thing we do is to convert 275 grams of ethylene glycol to moles. Here is the molecular formula. So you need your periodic table. Look at the atomic weights for these atoms, add them up, and what you should get here is 62.1 grams per mole. Here's your conversion unit to convert moles or grams to mole. So we use this here as our factor here, set this up so that this cancels here, and we end up with moles. So after you do the math here, you have 4.43 moles of ethylene glycol. The bottom line is 275 grams of ethylene glycol is equal to 4.43 moles of ethylene glycol. Remember, as chemists, we're always using moles as our unit. So now we have our equation. This is our equation here. So the change in temperature, notice this delta here, it's a Greek letter, means change. So the change in temperature is equal to 1.86 Celsius per mole times moles of particles. So here we go. This change in temperature is equal to minus 1.86. Notice we put a minus sign because it's a freezing point depression. We're going below zero. And we have here 4.43 moles, and since we have one particle, we multiply by 1, which is not shown here, and so after you do the math here, the freezing point of that solution is now minus 8.23 degrees Celsius and not 0. So the freezing point is lowered by 8.23 from 0 degrees C. So now you can see the benefit of putting ethylene glycol or antifreeze in your car, especially in the winter, because it does not allow the water to freeze at 0 degrees C, but some temperature below that, depending on the concentration of the solution. Let us look at another example here. So here, still freezing point depression, but now we're using potassium sulfate. So if you mixed potassium sulfate in 1,000 grams of water, what will be the effect on the freezing point? The key here is potassium sulfate will dissociate its ionic. So in water, it's going to dissociate. Remember we did that earlier. Water is a good solvent, good polar solvent. So you put an ionic compound such as potassium sulfate or sodium chloride in water, it's going to dissolve it by forming ions. So here we have 2 moles of potassium cation, K2. And we have 1 mole of this sulfate polyatomic anion. So this is all 1 polyatomic anion. So here we have 3 moles of particles. 3 moles. Okay, so that's key. That's key. So let us see if we can solve this problem. So here is the same problem. Now we have 275 grams of potassium sulfate in 1,000 grams of solution of water. Remember this now will give us 3 particles. And we have 275 grams of potassium sulfate. This is our conversion factor, or the important equation that we will be using. But first we need to convert the grams into moles. Here is the conversion. So get your periodic table again and look at potassium, find its atomic weight, multiply that by 2, sulfur, multiply that by 1, and of course oxygen, find that and multiply that by 4 and add that up, and what you'll get is 174.3 grams per mole. So that's the molecular weight of potassium sulfate, and here's your conversion factor. You set this up so that the grams cancel, you do the math, you end up with 1.58 moles of potassium sulfate. 1.58 moles of potassium sulfate. Then you apply that to your equation here. This is where the moles of particles will become very important. So here we have minus again because it's freezing point depression. As you can see here, freezing point depression. And of course here we have 1.58 moles, but now we have 3 particles. 3 particles, 2 potassium and 1 sulfate. After you do the math, you end up with minus 8.2 degrees as the freezing point of that solution. So it's no longer 0, degrees C, but it's minus negative 8.82 degrees C, freezing point depression. Let us look at another aspect here of colligative properties, and this is the boiling point elevation. Of course, as you know, that if you are in the kitchen and you're cooking, if you put water to boil and you put salt in it, the boiling point of that solution of salt and water is no longer 100 degrees C, but it's different. It's going to be higher than 100 degrees C. It's going to be hotter than 100 degrees C. Remember that 100 degrees C is a physical property of pure water. Pure water, that's the key. But if you start mixing pure water with a solute such as salt, that property changes. That's called boiling point elevation. So here it is. You mix any 1 mole, it will raise the temperature by 0.512, and here it is. So delta again is the change. TB here is for boiling. Here's the conversion factor here, or the equation of importance. Notice again, moles of particles. Moles of particles. So remember, the colligative properties depend only on the number of particles in solution. Number of particles. So we'll have to determine the number of particles. Let us see if we can solve that problem. So if we have here 275 grams of table salt. Table salt is NaCl. What will be the boiling point of that solution? So you have 1,000 grams of water, you add 275 grams of table salt in it, you put it on the burner, and you start boiling, and you put a thermometer in it after it's boiling. What will be the temperature? We know it will not be 100 degrees C. It will be different. And since we're talking here about boiling point elevation, it's going to be higher. So let's see if we can do this, apply this concept here. We have 275 grams. We know, first of all, we'll convert the grams to moles. Here's the conversion factor. So you need your periodic table. Add up the atomic weights here for sodium and chlorine. And what you'll get is 58.4 grams per mole. That's the molecular weight here. And this will be the equation that we'll set up so that these cancel out and we end up with moles. So once you do the math here, you end up with 4.71 moles of NaCl. 4.71 moles. Next, we utilize this equation here, and here's the key: moles of particles. How many particles are there in sodium chloride in water, a solution of water? We know that sodium chloride dissociates to give sodium plus, 1 particle, and Cl minus, another particle, so it's 2 particles. So using this equation here, delta T, this is a constant, and of course we do the math, we end up with 4.82 as the change in temperature. So therefore the boiling point of water that contains 4.71 moles of sodium chloride will be 104.8 degrees C and not 100 degrees C. The last concept here is that of osmosis. We are very familiar with osmosis, but let's discuss the concept first and then we apply that. So the concept here is, if you have a membrane and here is a bag, so to speak, that has a solution in it of sugar and water. Sugar and water. And placed outside is pure water. So it does not have any sugar outside. What you'll discover after some time is that the volume here increases. As you can see here, it increases. What happens is that the water molecules here go into that bag that contains the sugar solution. So the bottom line is pure solvent molecule, water molecules, enter this semi-permeable membrane and goes into this solution to dilute it. So in other words, the water goes from the exterior into an area that's of higher concentration for dilution. Key here is that it passes through a semi-permeable membrane. So semi-permeable membrane is one that allows solvent molecules, keyword solvent molecules, to pass through, go in or out. And if it goes in or out, that depends on the concentration of the two media. Let's see if we can explain that a little differently here. So here we have a membrane, semi-permeable membrane. Notice keyword semi-permeable. It will allow solvent molecules, only solvent molecules to pass, and not solute. And not solute. Let's see if we can apply that. And of course, one practical application here is having cucumber here and making pickles from cucumber. So we have here a pickle, and we place that in a solution of brine, which is really concentrated salt solution. Notice concentrated salt solution. So this area out here is concentrated salt. The area in here, in this cucumber here, has water, and the membrane would be right here, so the water molecules come out. So after some time, what you'll get is a pickle that actually looks like this, or a cucumber that looks like that, and of course we call it a pickle. So, as a summary, so a semi-permeable membrane is a membrane with tiny pores, big enough to allow solvent molecules. Keyword here is solvent and not solute. So we will not allow large solute molecules to pass through the semi-permeable membrane. Osmosis is a process where we have solvent molecules passing through a semi-permeable membrane. Again, solvent molecules passing through, and of course it depends on the concentration. So the solvent molecules move from the region of low solute concentration, less concentrated, to the high concentrated. So if you look at it as always trying to dilute the high concentration. And of course, osmotic pressure is the pressure that causes the solvent molecules to move from one area of concentration to the other. You probably heard of reverse osmosis, where we would take salt water, for example, or countries where there's lots of seawater. They take the salt water and they convert that to pure water. That's really reverse osmosis, where they apply pressure and reverse the process of osmosis, so the water molecules go in the opposite direction. And that's how you get pure water from salt water. And here is our last slide, and this is the practical importance, especially for the students who are in the medical field, dialysis. So as you know, if a patient has dialysis, the kidney is not working properly, and the kidney is there to take out the toxins. And so what happens is that the blood is passed through a system here that has a filter or a semi-permeable membrane, and of course as it passes through, here's a solution in the equipment, and because of the difference in concentration, it allows the toxins in the blood to pass into this area. And of course, what comes out is the blood comes out with less toxins. So this is a practical application of osmosis. This is the end of the chapter 6. So again, we'll have a quiz coming up on Thursday, which will be primarily your 5 questions on these aspects here in chapter 6, the last few chapters, sections in chapter 6. So make sure you go back and work some problems. There'll be a few problems, and of course a few definitions. So continue to study hard. We're getting close to the end of the semester. So hang in there and work consistently, and we'll make this together. Okay? Bye.